All right, thanks. Yeah, so just to remind you, so yesterday I told you a little bit about replicator dynamics and about games in finite populations. So today we apply what we know now to two different kinds of mechanisms for cooperation. So one mechanism is direct reciprocity, the other one is indirect reciprocity. I'm a little bit afraid that today you will get an overkill of me because I have 2 lectures today, but I hope it will be fine. As usual, if something is unclear, please just interrupt me. Everything should be clear, okay? All right. Yeah, so just to make sure what I mean by cooperation, I think most of you know, but there is a potential for misunderstanding because like what is cooperative, like there is this distinction between non-cooperative and cooperative game theory, and it actually has nothing to do with the cooperation that I'm now talking about. So I'm now talking about the cooperation that we consider in theoretical biology. And so it's this idea that I pay a cost to help someone else. And I guess every one of you can come up with many examples, but just to have some examples in mind, here are a few. So one is, for example, donating money to charities. Yeah, sorry. In some sense, yes. To be honest, I'm a little bit sloppy. I use these terms altruism and cooperation a little bit interchangeably. That's right. I guess I would rather consider this as mutualism sometimes. Yeah. But it's very good to ask. So like there are different terms out there that mean very similar things. So for the following, I mean cooperation is that I pay a cost to help someone else. Yeah, so one example is just I donate money to charities or I provide first aid. Another example that most of you might be familiar is, I see Nikhil shaking his head, acting as a referee for a journal or doing outreach, like things that perhaps you might not want to do, but still you realize it's the right thing to do and therefore you do it. Another important example is organizing a scientific meeting, and just to have an abstract example that has nothing to do with reality, say one on decisions, games, and evolution. So that's obviously is also quite a lot of work, and also it should count as cooperation. Thanks for those who feel that I talked about them. Yeah, and there are also multiple examples in the animal world. So these are quite famous examples. So for example, there are these fish called stickleback, and what they do is they sometimes swim in pairs. And what you then don't want to do is, like, you don't want to be the one who always swims first, because the one who swims first is usually also the one who would be eaten by a predator if there's a predator around the corner. So what Manfred Milinski showed there is that usually a stickleback, like, they take turns. So sometimes this fish would go first, sometimes this fish would go first. Now, there is one thing about this experiment that I like a lot, because I think it's very elegantly designed. Because like if I would have to design an experiment that shows that stickleback plays something like tit for tat, I mean, I would put 2 stickleback into a tank, and then I would just observe them, and then I would try to do some data analysis and try to find that there is indeed tit for tat going on. But that is not what Manfred Milinski did. Manfred Milinski put actually 1 fish only in the tank and a mirror. And he could adjust the angle of this mirror, and depending on the angle of the mirror, it would look to the fish as if this fish is ahead, or if this fish is back from the other one, from the virtual other one. And so in this way, he could get much clearer results on this effect. So this is really nice. Like, these kinds of experiments are always a bit tricky, because you need to show that really the conditions of a prisoner's dilemma are satisfied, like that there is really a cost and the benefit to all of these things. So actually all of these things, like also like the reciprocal food sharing vampire bats, it's actually quite difficult to really show convincingly that reciprocity is going on and not, for example, kin selection or some other mechanism of cooperation. So usually these things are quite tricky, but like these are, for example, 3 species where people argue that this is direct reciprocity. Yeah, and before we go on, like probably to most of you, like it's clear what I mean, that this is a puzzle. Like it's not exactly clear why we do this, but then if you look at it in a naive way, you might also say there's nothing puzzling about it, because like for example, it probably never happens to you that you donate to a charity, and then 1 second later, you ask yourself, why did I even do this? Like, this is really strange. Why would I do it? So to you, it's obvious why you do it. And there are at least 3 proximate explanations why you might actually cooperate. The first one is it just feels good. Like sometimes it just feels like a nice thing and you want to be a nice person, so therefore you do it. There is another explanation, like sometimes, I'm thinking of the reviewing a paper example here, you feel that there's some kind of social norm, like this is what a proper scientist should do. You want to be a proper scientist, so therefore you cooperate in such a situation. There's a further example, like some of these cooperative acts, for example, providing first aid. At least in Austria, there is actually a law that tells you that if you come to an emergency, you are obliged to provide first aid. So these are all proximate explanations, and you could, after seeing these explanations, you could say, okay, the problem of cooperation is solved. Like, these are explanations for cooperation. I just want to convince you that there is actually one more question to be asked. The one more question to be asked is, why do we have these particular emotions? Like, if cooperation really means that you pay a cost for someone else, and if we are a product of Darwinian evolution, we shouldn't have these emotions. Like, if we want to maximize our fitness, we should have emotions that tell us, well done, you didn't help someone. But we don't have these emotions. So the question is, why do we have these particular emotions? And the same thing is, like, why do we have these particular social norms? Could we have completely different social norms? Like, are there any restrictions on the social norms we have? And the same thing with institutions. Like, could there be arbitrary institutions, or are there some restrictions on institutions that we might have? And like, does evolution, for example, favor one set of emotions over another? And so in this sense, this is still a tricky problem that is worth exploring. Okay. All right, and just to make things a little bit more precise, let me revisit one example from yesterday. So the example from yesterday was this prisoner's dilemma, where there are 2 people that can either cooperate or defect. And the cooperation here means to pay a cost to provide a benefit to the other player, and defection means to do nothing. And if you, yes? No, no. The normal form game also is essentially the same, right? No, that's right. It's very good you asked. So I told you that my cooperation is not the same thing as cooperative and non-cooperative game theory. So I should actually tell you what it is. So what I will be talking about is actually a subset of non-cooperative game theory. So I will talk about cooperation, because you see here these normal form games, you see payoff matrices, you see players making independent decisions, so there are no coalitions whatsoever. So we are in the field of non-cooperative game theory, but unfortunately, I'm talking about cooperation within non-cooperative game theory. So this is a little bit confusing. Okay. All right, so this is the game that I'm interested in. And now what we saw yesterday, like if you're thinking in terms of classical game theory, you look at this game and you see, okay, cooperation is a dominated strategy. So whatever the co-player does, actually defection is the better thing to do. And as a result, also replicator dynamics tells you, like, if you look at the population, and even if they don't understand the game, even if they are not even aware that they are participating in the game, in the long run, they will evolve to defect. So if you think that the prisoner's dilemma is a proper model of human cooperation, then the prisoner's dilemma cannot explain why people cooperate. Okay, but so now we have this interesting paradox, like the simplest model for cooperation cannot explain cooperation, but at the same time we see cooperation in the world. So what does it, which kind of modification do we need to do? So the most likely answer why the prisoner's dilemma doesn't answer why we see cooperation in real life is that real life is not just a one-shot prisoner's dilemma. So then the natural question is, what is it then? Like, what are the aspects that we forgot about? And like, one aspect that we forgot about is that we might have forgotten that it makes a lot of sense to help siblings. I guess we had this quote from Haldane at some point that I would jump in the river and this kind of stuff. So that makes actually a lot of sense. So this is one mechanism for cooperation. Another mechanism for cooperation is that there might not only be selection at the individual level, But there might also be selection on some higher levels. So what I mean here is that even if there are different groups of players, like within each group, the cooperators might be disfavored. But if there is ever a war between different groups, those groups that have a lot of cooperators will be stronger than those groups that have very few cooperators. And also there are many models out there that try to understand in which situation this actually helps cooperation. So there is another explanation for cooperation, which is like usually, like with most people that we interact with, we interact actually more than once. And once you do this, cooperation might evolve by a mechanism called direct reciprocity. That's what I will actually talk about, the whole subsequent talk about. And there is, again, another mechanism which is like cooperation based on social norms, for example. Like I might want to cooperate, even if I never meet you again, I see that others observe what I do. I want to have a good reputation, so therefore I cooperate with you now. Yeah. Did you have a question? I'm totally agnostic. I'm just presenting here what is out there. Now, to which extent like group selection is the correct explanation for why we see cooperation in humans, I prefer not to make a statement. I mean, if you ask me, I have the sense it's probably not too strong in humans. So I have much more sympathy for direct and indirect reciprocity. Yeah, so these are some mechanisms for cooperation. Depending on how you count, there are more, and there are quite a few papers out there, review papers, that try to explain all the different mechanisms for cooperation. So for the remainder of this talk, I will actually talk about direct reciprocity. So this idea that cooperation can emerge if we interact repeatedly. So now, if you want to really make this notion precise that cooperation can evolve when we play repeatedly, I need to define a new game. So previously we had the prisoner's dilemma, now I need to define a new game. And the new game is the repeated prisoner's dilemma. And as always, when you define a game, like you need to define certain things, like who are the players, what are their possible actions, what is it that they know at the time when they make a decision, also when do players make a decision, and what are the payoffs. So usually these are the 5 ingredients in general that you need to define. Like in normal phone games, like the order of moves was not really important because there it was defined. Also, what you know is not really important. So these 2 ingredients were missing in normal phone games. But in general, you need to define these 5 things. So let me define these 5 things. So first, who are the players? Like I just assumed that the game takes place among 2 players. Then what are the actions that the players can choose? I just assume that the players play over many rounds, and in each round, they just play the prisoner's dilemma. So in each round, they can just cooperate or defect. What is the order of moves? Like you could make many assumptions here, but the standard assumption is that in each round, they move simultaneously. So what is it that they know when they make a decision? So when I'm in round 10, what is it that I know? I know everything that happened up to round 10. Plus, in addition, I understand the game. Like I know what the payoffs are and this kind of stuff. And the last thing is, what are the payoffs? So the payoffs you define based on the one-shot payoffs. So here, this pi I at t is just what is the payoff that I get in a given round. And now to define the payoffs of the entire repeated game, like there are 2 versions. The first version is like if the 2 of us play forever. I would just take t to be fixed, and then this is just the payoff that you get in the first t rounds, and you divide by t. So this is the average payoff that you get in the first t rounds, and then you take the limit of t going to infinity. So now, like mathematically, there can be sometimes problems because this limit does not necessarily always exist. In the examples that we will look at, this limit always exists. Okay, and there is another notion of payoff that you could define. So here up there, I said that players do not necessarily interact forever. Rather, after each round, there might be a probability that the game stops after this round. And so there is this parameter delta, which is called the continuation probability. So whenever we meet, with probability delta, there will be another round, and with probability 1 minus delta, the game stops. And so if you look at such a game, it follows that the expected length of the game actually follows a geometric distribution. And if you want to define payoffs in that game, it turns out that this is a reasonable definition. So actually, the round in T, you weigh it by how likely is it that you even reach this round. Okay. And this 1 minus delta here in front, it's just a normalization factor. So what this factor ensures is that if we always cooperate in every round, our payoff, according to this definition, is B minus C. And if we defect in every round, our payoff, according to this definition, is 0. So you can interpret payoffs here, you can compare payoffs here to the one-shot payoffs. Okay. All right, so this is the idea. We played a repeated business dilemma, so we play this one. Yeah, sorry. That's right. Yeah. That's right. So to be precise, so the probability that there are exact T rounds, I believe that's delta T, or perhaps the right way to motivate it is, what is the expected number of rounds? If you take this distribution, and it turns out it's 1 over 1 minus delta. And therefore, we just as we divided here by 1 over T, because T was here, the number of rounds, here we divide by 1 over 1 minus delta, which is then 1 minus delta. So this is usually the explanation for why people have this 1 minus delta here. So this delta T is just a discount of future payoffs. And this 1 minus delta just serves then as a normalization, which is kind of analogous to this normalization.
So the way I'm looking at it is, we need to stop rounds and then need to calculate the final payoff.
That's right.
Because if rounds keep happening, then we'll have to keep on updating. So I also multiply with the probability no more rounds.
That's right. Yeah. So this is a perfectly fine interpretation as well. Yeah. So the important thing here is mostly that you can compare these repeated game payoffs to the one-shot payoffs. So they are normalized. So if everyone cooperates, you would get the payoff here of B minus C. If I always defect and you always cooperate, I would get the payoff of B. So everything here is nicely comparable. And so up there you see the situation. So we play the repeated business lemma, then with probability delta we play another business lemma, then with probability delta we play another business lemma, and so on. All right. So this is the definition of the game. Now, after I've defined the game, I actually need to define what are the strategies. So up to now, actually strategies were very simple, like because we only talked about normal form games where you can only make one decision. And in such normal form games, strategies are really simple. Like I just need to tell you which action do I choose. Or in the worst case, I need to tell you what is the probability distribution with which I choose each action. So this is how complicated strategies could get. Now here in the repeated business lemma, strategies are more complicated because now my strategy is a rule that needs to tell me what do I do in every possible round. And importantly, what I do in round 10 might depend on everything that happened before. So now strategies can be very complicated. So now to make this a little bit more formal, let's write down some variables. So the first thing is like I use this variable a at t just to define what are the actions at time t. So the first component here is what is my action. The second component, for example, is what is Sylvia's action in round t. So for example, CD means I cooperated in this round, Sylvia defected. Now I define this tuple h of t, which is just everything that happened up to round t. So for example, in the first round, we might have both cooperated. In the second round, I cooperated, you defected. So we would just get this string of C's and D's that tells me everything I need to know about what happened up to round t. Capital H is just the set of all these possible histories. Like everything that could happen up to round 1, everything that could happen up to round 2, everything that could happen up to round 3, and so on. And after all these preparations, I'm now finally able to tell you what are strategies. So strategies are maps that take an arbitrary history as an input and that tell me, should I cooperate or defect? So you give me an arbitrary history of what happened in the game up to now. I tell you, will I cooperate or defect? And if I wanted to make it a little bit more general, it wouldn't even go into this set, but it would rather go into the probability distributions over C and D. So after every possible history, my strategy needs to tell me with which probability should I cooperate, with which probability should I defect. So those are the strategies in repeated games. All right, because this was a little bit abstract, let me give you some examples of simple strategies. So probably the most simple strategy is just the strategy that defects forever. So it starts defecting in the first round, then it defects forever. So that's the most natural analog of defection in a one-shot game, just the same strategy. It repeats what it would do in a one-shot game forever. So this is a very similar strategy also. You just cooperate forever. Now let's make it a little bit more complicated. There is a quite famous strategy called Grimm, which does the following, like it starts cooperating and it would continue cooperating as long as both of us cooperate. But if you defect once, I will defect forever. So this is a very strict form of reciprocity. And finally, this is another example, quite well known, tit for tat, which is in the first round, I give you the benefit of a doubt, I cooperate. And in all subsequent rounds, I do whatever you did in the previous round. So if you defected in the previous round, I defect. If you cooperated in the previous round, I cooperate. All right, so these are 4 very simple examples. Just keep in mind, like strategies could be arbitrarily more complicated. So for example, this is a very cumbersome example. For example, you could do the following thing. If the number of rounds played so far is a prime number, then I defect. Otherwise, if it's not a prime number, if it's a composite number, then I show like how far have I cooperated so far, how far have you cooperated so far. Only if you have cooperated twice as often as I did, then I would cooperate. Otherwise, I defect. And obviously, you could make it even more complicated. Like you could condition, for example, on arbitrary facts about number theory here, for example. Strategies here can be really complex. And as usual, if you have such a game, and for example, if you look at it from a static perspective, from a classical game theory perspective, the answer would be like, what are the possible equilibria? Like, what can we expect for such a game? And just to remind you, like, in the following, I will again use this notion of a Nash equilibrium. There are actually other, perhaps more appropriate equilibrium notions out there for repeated games, like, for example, subgame perfect equilibria. But here I will use the Nash equilibrium again. And by now you should already know, or perhaps you've always known, what is a Nash equilibrium. It's just a situation where, given the strategy of the opponent and given my strategy, I really have no incentive to change. I really cannot improve my payoff anymore. All right, so we would like to know what are the possible Nash equilibria of such repeated games. And you might have a guess that, I mean, this is complicated because the strategies here are really complicated. And it is indeed in some sense complicated, but in some sense it's also very easy because in the following sense. So suppose I already know what happens in a one-shot game. For example, in our case with the prisoner's dilemma, we know that in the prisoner's dilemma, the only thing that can happen is mutual defection. Then the question is, like, if you repeat it now according to the setup, is it ever the case that you can get anything else? So that's the baseline question that you ask here with the fork theorem. All right, so let's think about this question for a second. So usually what people do, it's quite useful to look at a two-dimensional representation like this. So remember, the game that we are looking at is B minus C, B, 0. And now this is my payoff. This here is your payoff. And if you only play this game once, there are actually 4 possible things that can happen. Like, one thing that could happen is we both defect and we both get a payoff of 0, 0. Another thing that could happen is we both cooperate and we both get the payoff of B minus C, B minus C. Another thing that could happen is I defect, you cooperate, well, then I get a benefit of B. You get a cost of minus C. So this would be perhaps here. And a last thing that could happen is I corporate U defect, and we would be up here, minus C. So these are the 4 possible payoffs that you can get in a one-shot game. Now the question is, what are even the possible payoffs that you could possibly get in a repeated game? And I would like to argue those are the payoffs in the convex hull of all these 4 points. Now, how do you see this? Like, now I need to convince you that these are really the points, the possible payoffs that you could get in a repeated game. Now, for example, to convince you, like how, like suppose I'm interested in this midway point here. How would I possibly get this payoff in a repeated game between those 2 players? And the trick here is, well, because it's exactly in the middle between 0 and 0 and B minus C, B minus C, what you could do is just play this sequence. So in the first round, we both corporate. In the second round, we both defect. In the third round, we both corporate. In the fourth round, we both defect, and so on forever. And if both players happen to have a strategy such that they play in this way, the average payoff that you would get over infinitely many rounds, for example, would be exactly here in the middle. And similar things, by the way, here I'm assuming that delta is really close to 1. Otherwise, it's a little bit more complicated to argue. And in a similar way, you can argue for every possible point here that you can somehow get it as a sequence of C's and D's. Not necessarily of a sequence where we always both corporate or both defect, so it can be a little bit more complicated. So sometimes, for example, for this point, you might to play this outcome for 2/3 of the rounds and this outcome for 1/3 of the rounds. But in general, because it's the convex hull, you can guarantee that there is always such a sequence of moves such that on average, players get a payoff in here. So in principle, the payoffs that you can get in this game are the payoffs that are given by this convex hull. So now if you ask me which payoffs can you sustain in equilibrium, the first trivial observation is, well, can you sustain this payoff? And the answer is no, no way, because like this payoff is in principle infeasible. Like there's no way how players can even play to get this average payoff. It's just not possible in this game. All right, so one obvious requirement. So even in the repeated game, equilibrium payoffs need to be feasible. And by feasible, I mean exactly like, there needs to be a possible outcome of this repeated game that would actually lead to this average payoff. And yeah, sorry. I mean, it's the same thing. Like the way how I argued here, so this is the example that I made is the exact midpoint. And now the way how I argued is that if I play the sequence, I get exactly to the midpoint. But if you are precise, this argument only holds for delta equals to 1. If you don't have delta equals to 1, then this round you have for sure. So this has a weight of 1. This one has a weight of delta. This has a weight of delta squared. So this has a weight of delta to the 3. So here, this payoff, like the C's are slightly more weighted than the D's. So if you look at it with delta, so this sequence would actually not produce the midpoint, but rather something, a point that is up there. Yeah, that's right, yeah. But I mean, I should also say that in this literature, usually what people look at is the limit of delta going to 1.
Even for finite round, it may not work. I mean, it depends on whether you truncate it at odd or even number of rounds. Because the half will not come, the average half will not come.
That's right. But like if you have a delta, like you don't have a possibility to truncate it always at the even numbers. Like yeah. All right. Yeah, please.
I think the 1 minus delta, if you multiply it with the deltas, then it makes them convex combination.
Sure, but still, so of course I would have to multiply this by 1 minus delta. But still, like what you see is that the C's, like if you add up all entries that have mutual C's, and if you add up the weights, you would get a larger sum than if you add up all the weights that you have with mutual Ds. And therefore, the average payoff of this sequence, if you have a delta smaller than 1, it wouldn't give you half B minus C.
Sure, but it will always lie in the convex.
That's right, yeah, that's right. So it will always be, so the fact that it's always, and trivially true, it will always be in a convex half, yes. Okay. So this is one obvious requirement. Like, obviously you cannot get an equilibrium payoff that is up here. It's impossible. Now I would like to convince you of another obvious requirement. And I argue the other obvious requirement is that equilibrium payoffs cannot be here. And similarly, equilibrium payoffs cannot be here. And now why is that? The reason why is that is, suppose I would get a payoff here. So I would get actually a negative payoff. Then if you just look at the payoff matrix, I mean, I can always play D. And if I play D, at least I get 0. So there's no way how in equilibrium I could get a negative payoff. Okay? So for this kind of argument, you can exclude these two regions. So this is the other obvious requirement. So this is sometimes called payoffs need to be individually rational. And what is meant exactly is that in this case that I need to get at least a payoff of 0, because the payoff of 0 is the payoff that I can guarantee myself. Like no matter what you do, I can always at least guarantee myself a payoff of 0. Yeah. Yeah. Okay, there are two. So the question is, if I play this sequence, could the payoffs be negative? I mean, in the way how, in general, yes, but in how we, given how we actually chosen these parameters, it would actually be B minus C over 2. Because like in half of the rounds you get B minus C, in half of the rounds you get 0. And therefore, the overall payoff that you would get is B minus C over 2. And because B is larger than C, this payoff is actually positive. So this sequence could actually happen perhaps in equilibrium. Like we haven't ruled out this sequence yet. But also like, keep in mind that when I defined feasible payoffs, I wasn't even worrying yet whether this thing is in equilibrium. I was just interested whether this thing can occur in principle, like whether we could play such that we would get this payoff. Yeah. That's right. It's absolutely possible that you can design a strategy that gives you a negative payoff against a given opponent. For example, if my opponent is playing, I don't know, all D, for example, it's very easy to design a strategy such that I get a negative payoff, for example, by playing all C. I guess the only point that I'm making here is such a strategy, like this strategy profile that I play all C, you play all D, it cannot be in equilibrium. It cannot be in equilibrium. Yeah. Because like if I were in a situation where I play all C, you play all D, I mean, there is a better response. Like I can play all D as well. And then I get a payoff of 0 instead of a payoff of minus C. Yeah.
I was just thinking that because we're thinking of match equilibria, it would have to give a negative that it plays itself, which I don't think can happen.
That's right. We will see in a second that this cannot happen. Yeah. So at the moment, I've only told you necessary conditions for something to be a Nash equilibrium. Like for a payoff to be feasible in Nash equilibrium, like it cannot be up there, it cannot be in here. So now I need to give you a sufficient condition for something, so for some payoff to be a Nash equilibrium. And it turns out that this is now easy because these two obvious requirements is actually everything that you need. So if you have a payoff that is neither outside of this convex hull, nor it is in this region, so for example, this payoff here, then this can be an equilibrium. There is an equilibrium in which players would get exactly this payoff. And the proof roughly goes as follows. Like, if you have a point in here, let's again argue with this midpoint here. We already know there is a sequence of actions that players could use such that on average they actually reach this payoff. Now I need to construct strategies that make sure that this would be an equilibrium. And the strategy is as follows. I play such that I would follow this sequence for as long as my co-player follows this sequence. And once my co-player deviates, I will defect forever. And then the idea is, well, if you follow the sequence, you get a payoff of b minus c over 2 in the long run. But if at some point I defect, for example, in round 3, in round 2, instead of in round 3, instead of cooperating, I start defecting here. My co-player would switch to relentless defection from then on. So the best thing that I could get from then on is actually a payoff of 0. And 0 is smaller than b minus c over 2. So this is the basic idea why everything here in this region can actually be achieved by an equilibrium of the repeated game. Okay? Yeah?
So the concept of equilibrium you're using here, is it Nash equilibrium or something perfect?
Here I was just talking about Nash equilibrium. There are analogous versions of this Fogg theorem, of course, for subgame perfection. That's right, yeah. So tit for tat would be a Nash equilibrium, it's not subgame perfect. So just for everyone else who perhaps do not know what is subgame perfect. So Nash equilibrium just means that you play optimally along what is called the equilibrium path. So as long as we do what we are prescribed to do, I play optimally. So this is what Nash equilibrium requires me to do. There is a stronger notion of equilibrium, which is called subgame perfection. And this requires me not only to play optimally along the equilibrium path, so optimally as long as we play, for example, this thing, but also optimally along every other path that could possibly arise during the game. So you play optimally for every possible subhistory that you could possibly visit. Yeah, and so to make things simple here, I only talked about Nash equilibrium. There is this stronger version of subgame perfection out there, and there is a very similar version of the Fogg theorem for subgame perfection. Yeah.
Suppose I take alternating game or let's say stochastic game between two business dilemmas.
Yeah.
Then this kind of theorem works?
Okay. So the question now is, we looked at the repeated business dilemma, so players play the same game over and over again. So there is a more complicated class of games out there, which is called stochastic games, where you don't play the same game over and over again. Rather, the game that you play in the next round might actually depend on what happened in the previous round. So this class of games is called stochastic games. Then the question is, like, does something like the Fogg theorem also hold for stochastic games? And I believe in simple versions of stochastic games, it does. It's just that stochastic games make everything more complicated. And as far as I know, even existence of Nash equilibria is not proven yet for the most general class of stochastic games. All right. Yeah, so this above is, again, the illustration. So this is the possible equilibrium payoffs that you could have in a repeated game. Yeah, and the proof of this theorem, I mean, I sketched it to you. It's kind of constructed. Like for each payoff here, you can actually explicitly construct a strategy that would give you this equilibrium payoff. And now, in principle, like this Fogg theorem is good news because it tells you like all the possible equilibrium payoffs that you could get. So this tells you actually quite a lot. But also, from a certain perspective, it's bad news because there, in some sense, there are just too many equilibria. Like it's almost like anything goes. Like you give me a payoff here in this convex hull, I tell you, yeah, sure. So that kind of makes it a little bit hard to predict what will happen in such a game because you could justify almost any outcome if what you care about is just the Nash equilibrium of the game or the subgame perfect equilibrium of the game. Yeah. So in particular, if you are now in an experiment on the repeated business lemma, like the Fogg theorem wouldn't tell you how to play the game because like all possible things could happen in this game. So if you have any aspiration to predict what would happen in a repeated business lemma, the Fogg theorem is not really useful. Well, it excludes some things. So obviously some things cannot happen. So I would believe that at this point you would never see an experiment, but it leaves all of this area like unpredicted. All right. So if you're really interested in the naive question, perhaps, what is the best strategy in a repeated business lemma? You need another approach. And one quite famous approach is this approach by Axelrod. So Robert Axelrod is a political scientist. He was in the end of the 70s, beginning of the 80s. He was very interested in what is the best strategy to play the repeated pistis lemma. And his approach was, why don't I ask experts? So he asked 14 experts, like political scientists or psychologists or mathematicians or economists. And he told them, by the way, I organize a tournament. Please tell me what is the strategy that you think is the best strategy of the repeated pistis lemma. All these strategies will play against each other, and then we determine the winner. So all participants knew what are the possible payoffs in each game. They didn't know what is, like, for how long the game is played, for example. In the tournament, it happened that the game is played for 200 rounds, but the participants didn't know that. Yeah, and like, if you look at the 14 strategies that were submitted, like, some of them were quite sophisticated. Like, some of them really used the first few rounds to try to build a model of the opponent and then to exploit this model of the opponent. And so quite sophisticated. But interestingly, like, the simplest submitted strategy won the tournament, and that's tit for tat. Simplest here in how long the code is for the strategy, because actually it was a computer tournament. So people had to submit their strategy as code, and the shortest code actually won, tit for tat. And just to give you an intuition for why tit for tat might be a good strategy, well, you might look at the game between tit for tat, like, suppose you know that your co-player is tit for tat, and you might ask yourself, well, should I play tit for tat or should I play all D, for example? And for example, if you play all D, well, in the first round, you benefit. You get a benefit of B instead of what you could get, B minus C. Okay? But then, because tit for tat always repeats what the co-player did in the previous round, in the next round, they both defect. So they both get a payoff of 0. Then in the next round, they both defect. They get a payoff of 0. And so on. So the average payoff, according to the formula that I gave you in the beginning, if you assume some discounting, is that all D gets a payoff of 1 minus delta times B, and tit for tat gets a payoff of minus 1 minus delta of C. In particular, all D gets a slightly higher payoff than tit for tat. But now the relevant question is, like, if I already know that my co-player plays tit for tat, is it optimal to also play all D and to get this small pairwise advantage? And to check that, we just look what would happen if two tit for tat players would play against each other. Well, they would cooperate indefinitely. And also here you can compute what are the players' payoffs, like both get the payoff of B minus C. And now if you want to know when is tit for tat a Nash equilibrium, or in this case rather, when is tit for tat a better response against itself than all D, you would need to compare this B minus C. So this is what you get against tit for tat if you also play tit for tat, to this 1 minus delta times B. This is what you would get if you deviated and played all D instead. And so you would make this comparison. Tit for tat is a better response against itself than all D, if this inequality holds. And you can solve this for delta. So it just needs to hold that delta is larger than C over B. So this would tell you if the game is just repeated sufficiently often, like if there is a sufficiently good chance to meet the other person again, tit for tat is a better response against itself than all D. Or in evolutionary terms, a homogeneous population of tit for tat players cannot be invaded by all D. Yeah, please. Oh.
Both the players playing tit for tat, is it not dependent upon the initial action that I'm choosing? Because since you're choosing CC for both the cases, suppose I choose CD, then it will be like DC or in the next round.
That's right. Tit for tat is, you're absolutely right. Tit for tat is very sensitive to what happens in the very first round. It so happens that when people usually use the term tit for tat, they have implicitly in mind that you start with cooperation. So this is what this arrow here on the left side indicates. You have this understanding that in the very first round, players would cooperate. There are versions of tit for tat that would defect in the first round. For example, there is this strategy called suspicious tit for tat, which is exactly like tit for tat, just it would defect in the very first round. And now if suspicious tit for tat plays against suspicious tit for tat, for example, they would defect forever. Because in the first round they defect and then they copy what the co-player did in the previous round, so they defect forever. So things very much, even if in all subsequent rounds you just copy what the co-player did in the previous round, it's very sensitive on what happened in the first round. All right, so this might give you a possible explanation why you might see something like tit for tat, for example, in sticklebacks. All right. Now, the paper of Axelrod and Hamilton, has been a huge influence on the field. There is a whole field called evolution of cooperation, which was actually the title of this Axelrod and Hamilton paper, just following this paper. But still, you might want to ask, okay, how confident are we that tit for tat is the answer? And there are two reasons why you might doubt that tit for tat is really the best strategy to play this game. One disadvantage, and that's actually related to your question, is that tit for tat is very sensitive to errors. What I mean here is that, well, in the table that I've shown you before, I assumed that tit for tat really plays always according to tit for tat, and then they would cooperate forever. But now, suppose there is always a small chance that even if I want to cooperate, perhaps I don't have time, or there are some other reasons that I just cannot cooperate. So there is a small probability that I would commit an error. My strategy would tell me to cooperate in this situation, but because of chance, I just happen to defect. The bad thing is, once there is defection, you would have these vendettas. So the next round, my co-player would defect, the round after, I would defect, and so on. So this is exactly the reason why actually tit for tat is not subgame perfect, because actually after this thing happened, what happens afterwards is very bad. Actually, if you ever experience such an error, you would like to deviate from tit for tat, because you really would like to avoid these kinds of vendettas. All right, another argument that why you might be unhappy with this result is, I mean, obviously, the result of such a tournament depends on which strategies were submitted. And even Axelrod himself noted, he reanalyzed the outcome of the game and he checked, is tit for tat really the best strategy? Or could I have added another strategy which would have won the tournament if it was participating? And he realized himself, well, for those 14 strategies, there would have been an even better strategy, which happened to be tit for two tat. So this is, I only defect if you defected against me twice in a row. Yep, please.
One more question is that initially you said the participants did not know the number of rounds for which the game is played. So suppose that is being announced to all the participants, will things change?
It's a good question, how things would change in such a tournament. It's actually not very trivial to respond to, because this experiment, as far as I'm aware, this experiment was never done in a setup where people actually knew the number of rounds. From an equilibrium perspective, it would make a huge difference, because if you know beforehand what is the last round, you immediately have an incentive to defect in the last round, because there's nothing that will follow. So you really have no incentive to defect in the last round. But because you already know, now again, you need common knowledge of rationality. If I am smart and I know my co-player is smart, I already know that my co-player will defect in the last round anyway. So therefore, I can also defect in the second to last round, because there will really be no punishment in the last round. And therefore, if you believe in common knowledge of rationality, you would see defection all the way to the first round. So in this theoretical sense, it makes a huge difference whether you know a number of rounds beforehand. I'm not sure whether Axelrod actually tried tit for free tat, but of course one could check. Yeah. I mean, that's in general the problem with these kinds of things. There are just uncountably many strategies. So, and in any tournament you can just do with countably many strategies. So it's a little bit unclear how you can generalize the insights that you get from such a tournament. Yeah.
Maybe the fact that tit-for-tat based tit-for-tat in this setting, something to this, because if I remember right, there was one more paper, right, where Axelrod Hamilton proved that tit-for-tat is the best ESS strategy for this dilemma game, given shadow feature is greater than some limit. So they are making a very general claim that tit-for-tat is the ESS strategy. So how can it be that tit-for-tat beats tit-for-tat answer?
Yeah. To be honest, I don't know this paper that you're referring to. There is another paper that shows that in a game without errors and infinitely repeated, there is actually no ESS. Because like the idea is that there are always neutral invasions to any given strategy that might be in the population. There are always neutral invasions that play exactly like this strategy along the equilibrium path, but that would do something completely crazy if you ever did something deviated from the equilibrium path. Yeah. Yeah, I guess what I'm telling you is that at least for the standard version of the repeated persistence lemma, there is no ESS. Things change, by the way, if there are errors. So once there are errors, there can be an ESS, because then every possible history is reached with positive probability. That's what is important to construct ESSs. But if there are no errors, there are just some histories that you will never see, because like, given the two strategies, for example, given that we play these kinds of strategies, the game will never test you what you would do after 5 rounds of mutual defection. So in particular, you could easily deviate in what the strategy prescribes you to do after 5 rounds of defection. It wouldn't affect your immediate payoffs. So there would always be this kind of neutral invasion. All right. So after this argument, you might think it would be nice to have some kind of more objective results that do not depend too much on which strategies you allow. And this strategy, I mean, obviously, you would like to do it with the set of all strategies, but that's just undoable, at least so far. Still you would like to, so you will work with a subset of strategies, but still you would like to have an interesting subset of strategies. So the subset should be sufficiently rich that you can map most interesting behaviors within this subset. So one very popular subset is the subset of memory 1 strategies. And that's the subset of strategies where what I do in the next round, like in principle, it could depend on everything that happened in previous rounds. But for memory 1 strategies, it really only depends on what happened in the previous round. I forgot everything that has happened before. Yep. That's right. Yeah. That's right. Yeah, I guess I wasn't exactly making this statement. I guess what is true that if you have a game with errors and I play tit for tat, then it actually happens that tit for two tat is a better response. So tit for tat is really only a Nash equilibrium if there are no errors at all. Now, to which extent you can conclude from the fact that this is an equilibrium that something else is also an equilibrium, I don't know too many results out there, but perhaps we can discuss afterwards. Yeah, so then the question is like, if we work with this, yeah, please. That's right. So the intuition is the following. Suppose we play tit for tat. And suppose there are no errors whatsoever. Then we would always cooperate and so on. And we both would get an average payoff of B minus C. And that's perfectly fine. If there are no errors, you can actually prove that there is no other strategy that can do better than getting a payoff of B minus C. So if there are no errors, it's really true that there is no profitable deviation from tit for tat. But now suppose there is a very tiny probability of having an error. Like there's this epsilon which might approach 0. So it might happen that you enter this situation. C, C, and so on. But now, for some reason, one player defects. And then the question, so this would be now what is called off the equilibrium path. So along the equilibrium path, if everyone always plays as prescribed by the strategy, you would never see such a history. But if there are errors, such a history could occur. And what I would like to argue is that once you see this history, it's better not to proceed with the strategy tit for tat. Rather, if you proceed now by playing tit for tat, players would now this alternation between cooperation and defection, so they would get a payoff of B minus C over 2. A better response for this player would actually be, to cooperate instead, because then from then on they would cooperate forever. Yeah, please. That's right. I really like the mood today. We have a very cooperative mood today. Those are all great questions. So the question here is, okay, but I mean, why would I assume that only the first player makes errors? It could also be that the second player makes errors. So in particular here, it could have happened that this player actually wanted to defect, but perhaps he made an error again. So perhaps this happened, and then we are perfectly fine again. Now, just the problem is, there's no guarantee that this player would be the next player to make an error. And even there is no guarantee that, that things will play out nicely. So for example, if this player is not the player who makes the next error, but perhaps this player makes 2 errors in a row, then the situation is even worse. Then you get mutual defection for quite a long time. And what you can actually show, if you really look at a game with errors and let the error rate go to 0, you can show that all of the 4 possible outcomes occur with equal frequency. So 2 tit-for-tat players against each other, if there are errors that are very small, they would get approximately a payoff of B minus C over 2. Yeah, awesome. All right, so this is the strategy space that I want to talk about now. So this is the space of memory 1 strategies. This strategy space needs to tell you what do I do in the very first round, where I don't have any previous history that I could condition on. So P0 is the probability that I cooperate in the very first round. And then, for example, PCD is my probability to cooperate, given that in the previous round I cooperated, you defected, and so on. So it's this element of, it's this 5-dimensional vector. All right? And now we should convince us that this is an interesting strategy space. So in particular, it would be nice if this strategy space contains some interesting strategies. And it does. Like, for example, it contains the strategy all D. It's just the vector that always cooperates with 0 probability. And it also contains the strategy tit for tat, because tit for tat is just, in the very first round, you have a cooperation probability of 1. And then you have a cooperation probability of 1, if and only if the co-player cooperated in the previous round. So, for example, so tit for tat in all D you can represent within the space of memory 1 strategies. You cannot represent all interesting strategies in the space of memory 1 strategies. For example, this tit for 2 tats, that would require 2 rounds of memory. All right, so why are people interested in this memory 1 space? Like, first, because many interesting strategies are in there. And the other advantage is you can easily compute payoffs when 2 memory 1 strategies play against each other. And perhaps we use a few minutes to illustrate how. So suppose you have 2 memory 1 strategies. So the first strategy is this payoff, this strategy P, which has P0, PCC, PCD, PDC, and PDD. And the other strategy, my co-player plays the strategy Q, which is Q0, QCC, QCD, QDC, and QDD. And now I would like to know, so this could be, for example, tit for tat versus tit for tat, or it could be tit for tat versus all D, like any numbers that you might choose. Now the question is, like, if I have these 2 strategies, how can I compute the payoff that they would get against each other? And the trick is to, because everything only happens on the previous round, you can actually interpret the game between these 2 players as a Markov chain. So in particular, like what you can do is, The state space of this Markov chain is what happens in any given round. So what happens in any given round could be CC, or CD, or DC, or DD. So I corporate, you defected, and so on. And the question that I ask, given that I know the outcome of the previous round, what is the probability that I would see a CC in the next round, a CD, a DC, and a DD? And all right. So now I need to populate this transition matrix. So given I know that the previous outcome was CC, we both corporate. What is the probability that we both will corporate in the next round? Does anyone know? That's right. For TFT, if the two players were tit for tat, it would be a clear one. But what is the general formula? Yes, who said it? Perfect. So because the previous outcome was CC, I would use this cooperation probability in the next round. Also, my co-player actually sees this exactly the same history. He would use this cooperation probability in the next round. We both need to cooperate. We both make independent decisions. So it's just the product of PCC times QCC. Similar, if I want me to cooperate in the next round, my co-player to defect, what would be the transition probability? Exactly, yeah, it seems like quite a few people said this. So it's PCC, I still need to cooperate. The relevant cooperation probability is PCC because this is what happened in the previous round. My co-player needs to defect, it's 1 minus QCC. And so on. Perhaps, so I guess now it's clear how you will fill this transition matrix. Perhaps the only interesting case is, for example, here, like what happens if the previous outcome was CD? I mean, I want to know what is the probability that we both cooperate in the next round. For me, the relevant cooperation probability is CD. But for my co-player, the relevant cooperation probability is DC. Because for him, it looks the other way around. Like in the previous round, I cooperated, he defected. So from his perspective, it looks as if he defected and I cooperated. So that's perhaps the only subtlety that you have here. Otherwise, it's straightforward to do this transition matrix. And now, given that you have this transition matrix, you can actually compute explicitly the player's payoffs. Now, if delta is smaller than 1, you need to do a little bit work. So if the continuation probability is smaller than 1, you need to do a little bit of work, but it's still possible. If delta approaches 1, so if there are actually infinitely many games, you can derive the payoffs exactly from this transition matrix. Namely, by noting that, for the moment, assume that all entries here are strictly between 0 and 1. So this transition matrix will actually be what is called positive. And for positive transition matrices, you can show that the dynamics in the long run converges to an invariant stationary distribution. So in the long run, like, of course, in the beginning, it might depend on what players do in the first round. But over time, like the first round really becomes irrelevant. And in the long run, you will see some stationary probabilities that tell you like how likely are we see players to play CC, how likely are we to see them to play CD, DC, and DD. Okay, so this is, I mean, if you want to know how to compute this, it's just a left eigenvector of this matrix with respect to eigenvalue 1, because you want to solve this kind of equation. Okay. And now if you have this vector, it really becomes easy to compute payoffs, because if I want to know my own payoff, well, I get a payoff of B minus C if we both cooperated. The probability that we both cooperate in the long run is VCC, so times VCC. I get a payoff of minus C if I cooperate, you defected. The probability that this outcome occurs is VCD in the long run, and so on. Okay, so this is the nice thing about these memory 1 strategies. It becomes kind of easy to compute the payoff of one strategy against another. And just to appreciate this, compare how easy it is to compute payoffs here to how complicated it would be to compute payoffs if players adopted one of these strategies that I mentioned in the earlier rounds, like you defect whenever the round number is a prime number, and otherwise you check all possible things. Then it would be really hard to compute payoffs explicitly. Yeah?
So if any of the entries of PCC, PCD are 0 or 1,
yeah,
then you don't necessarily have a positive matrix.
That's right.
Yeah.
Yeah, so even if entries are, even if some of these entries are 0 or 1, you still might be fine because perhaps a power of this matrix is positive. So even then you can use Perron Frobenius. So this is the result that there would be a unique stationary distribution. But it can happen but in principle it can also happen that there are multiple absorbing states. And I mean, a very interesting example, for example, is exactly this tit for tat versus tit for tat. So for tit for tat versus tit for tat, the transition matrix would look like this. If we both cooperate, there is a probability of 1 that we will cooperate again. If the previous outcome was CD, in the next round it will be DC. So this happens to be the transition matrix for tit for tat versus tit for tat. So there are plenty of zeros in here, which makes things a little bit problematic. But it's even more problematic, there are multiple absorbing states. So for example, this is an absorbing state. This is an absorbing state. And like the collection of these two is actually an absorbing state. So here it really depends. You can still compute payoffs, but now you really need to know what happens in the first round. All right. Yeah, so this is what I just wanted to tell you. Memory 1 strategies are really nice because you can compute payoffs. This is how you do it. All right, so now that we know, okay, there's this interesting space of memory 1 strategies, now we might be interested in seeing, okay, like if we now do evolution in the space of memory 1 strategies, who would be the winner? And so this was done a little bit more than 30 years ago by Novak and Sigmund. So they looked exactly at computer simulations of something that is similar to the Moran process, but not exactly the Moran process, on the space of all memory 1 strategies. So they would have a population initially, like all the players perhaps play random strategies. Then in each time step, one player can perhaps compare its payoff to the payoff of another player and then imitate the other player if the other player is more successful. Also, every once in a while, there would be a mutation, and the mutation would just introduce a random new memory 1 strategy. And so they did these kinds of simulations. And what they see in the end is they see that evolutionary trajectories usually look like this. So this is the average. So here they only report. So here on the x-axis is time, what you see over the course of the simulation on average. On the y-axis is these four, P1 is PCC, P2 is PCD, P3 is PDC, and P4 is PDD. So it's those 4 entries of memory 1 strategies, if you ignore the first round. And what you see here in the end is that the strategy that wins in the end, it's very likely to cooperate after mutual cooperation. It's very likely to defect after CD. It's very likely to defect after DC, but it's very likely to cooperate after mutual defection. So the winner in their setup is kind of 1, 0, 0, 1. And they give this nice interpretation, like this strategy pretty much comes out of nowhere, like why would this strategy win? The intuitive interpretation that they give is the following. Like if you order payoff according to how much you like them, so B is better than B minus C, is better than 0, is better than minus C, then you could be happy if you get one of these payoffs, so then you are happy. And if you get one of these, you are unhappy. So in particular, like if you got a payoff of B, you just continue what you were doing. Like to get a payoff of B, you were defecting before, so you also defect in the next round. B minus C is still a good payoff, so you still continue what you were doing. To get B minus C, you were cooperating, so you just continue to cooperate. And here it's just the other way around. So that's actually why this strategy is called win, stay, lose, shift. Like if you're happy, you stay. If you're unhappy, you shift. And that's the interpretation that they give why this strategy is successful. There is a more formal explanation why this strategy actually happens to be successful. The more formal explanation is because win, stay, lose, shift is subgame perfect, whereas tit for tat, for example, is not. So in particular, even if there are errors, this strategy is good, whereas tit for tat is not. All right. Yeah, by the way, there's one more condition that I need to tell you. So Wien-Zillow shift is not stable for all possible B's and C's. So it needs to be the case that the benefit is at least twice the cost. Otherwise, it won't be sublinked. All right, yeah, this is not important. Yeah, now, okay, like people, as I told you, like people have been doing these kinds of things for many years, like the evolution of cooperation. This article has been around for more than 40 years. So people have done quite a lot of simulations with this kind of setup. And I guess in the beginning of 2010s, people largely believe that if you run a simulation with the repeated Peirce dilemma, then most likely what you see is mutual cooperation. Like perhaps you see a different strategy winning, but usually what you get is mutual cooperation. And kind of the repeated Peirce dilemma by now is a little bit boring. I mean, there is actually this interesting anecdote. Like I was actually writing my master thesis with Carl Sigmund on the repeated Peirce dilemma. Then I wanted to do my PhD with Carl Sigmund. And on one of the first days, Carl Sigmund told me, yeah, I know your master thesis was on the repeated Peirce dilemma, but you know, like people are not interested in it anymore. There's no market for the Peirce dilemma anymore. So for your PhD, you should do something else. And in fact, for my PhD, I did do something else. And that was actually before 2010. It just turns out that a very interesting thing has been observed in 2012. And the very interesting thing has been observed by a computer scientist called William Press and a physicist, Freeman Dyson. Freeman Dyson, I believe, when he actually wrote this paper was 92. So it was really surprising to the people. I mean, no one saw this paper coming. So what is it that this paper does? Yeah, those are the two people. The paper does prove the following theorem. So now bear with me. Suppose we look at an infinitely repeated Peirce dilemma with delta equals to 1. Okay, so we have been doing this for quite a while. You know what an infinitely repeated Peirce dilemma is. Now, suppose I can find magically some constants alpha, beta, gamma, such that I can write my payoff matrix, my conditional cooperation probabilities as such. Like it's not like, obviously I cannot choose arbitrary alphas and betas and gammas because like whatever is the outcome here, it must be always between 0 and 1 because these need to be cooperation probabilities. So from the outset, it's not even clear whether there are such alpha, beta, and gamma such that these would be reasonable cooperation probabilities. But for the moment, just accept that if I can do this, what happens? And what does happen is that payoffs will satisfy such a linear relationship. So alpha times my payoff plus beta times your payoff plus gamma is equal to 0. So the most natural reaction that you might have is, and by the way, strategies that can be written in this form are called serially determined strategies. So the most natural reaction that you might have by now is, so what? Like, why would I care? Like, okay, like, I mean, there is a linear relationship between payoffs. So what? Just to illustrate what this even means. So this is what you would usually see in a repeated Peirce dilemma. So what you would usually see if a strategy is not a serially determined strategy. What you would usually see, so for example, here I give this example that my strategy is fixed to Wien-Zillow shift. And I ask myself, what are all the possible payoffs that could arise if my co-player can play an arbitrary strategy? And here, in this, for creating this figure, I just simulated 1,000 random strategies. I checked what are the possible payoffs that might arise. And you see here the possible payoffs are in this convex set. Okay. Now, what happens if I happen to play a zero determinant strategy? It just so happens that like this convex set degenerates, it becomes a line. Still, you might ask yourself, okay, so what? Like there's nothing particularly nice about this line. And it's true, there's nothing particularly special about this line. But there are lines that are much more interesting. I would like to argue that this line is a very interesting one. Let me tell you why. So this line has two interesting properties. The first property is like, so I'm now playing this zero determinant strategy. So I'm getting this payoff. And one very interesting thing that you might see about this line is, well, it's always below the diagonal, except for here. Here it's on the diagonal, but otherwise it's always below the diagonal. So what does this mean? It means that I always get at least the payoff that you get. And usually I get a higher payoff than you get. Okay? So this is one interesting property of this strategy. This strategy would guarantee that I always get at least your payoff. And the second interesting property about this strategy is, like now from the perspective of my opponent, suppose, would like to maximize his or her payoff. So this opponent would ask itself, okay, given that payoffs are guaranteed to be on this line, where can I maximize my payoff? It turns out he would maximize his payoff right here. And that actually, like if my opponent actually tries to maximize his payoff, the payoffs are most unfair. By the way, also, what is it that the co-player needs to do to maximize his payoff? He needs to cooperate all the time. So these strategies has these two very interesting properties. I try to kind of exploit my opponent, like I try to be always better. And second, I do it in such a smart way that my opponent still would like to cooperate all the time. And because of these two interesting properties, these strategies have a name. They're called extortionate zero determinant strategies. All right? And like the interesting thing that you can note is like who can control this line? It's completely you. Like the only thing that you need to do is find alphas, betas, and gammas such that you like this line. And I guess what Press and Dyson showed also is that you can find such numbers. And I guess this was really a huge surprise because like repeated business lemma was kind of a metaphor for mutual cooperation, like whatever you do in the end, everyone mutually cooperates. So this is pretty much the opposite of mutual cooperation. Yes, please.
Alpha, beta, gamma, are these unique?
No. Yeah. So even for a given line, you can usually like find infinitely many alpha, betas, and gammas that would give rise to such a line. And in particular, like there could be many similar lines, like one where you just slightly change the slope here. But even for a given line, even if you fix the slope and given that you fix the intersection point here, I believe it's a one-dimensional set of strategies that can give you this line. In general, like if you allow for all strategies that also have different slopes but are always below the diagonal, I believe it's a two-dimensional set within this four-dimensional set of memory one strategies. Yeah, so this was a huge surprise. There was also an interesting story how they even came up with this. Because they didn't wake up and said to each other, well, let's look for zero-determinant strategies. We don't know what this is and whether it exists, but let's look for it. So instead what happened is that William Press, he was actually try to find a simple algorithm to determine whether a given strategy is Nash or not Nash. And he is a computer scientist, so he just wrote some code and tested this program. And what he realized is that this code would always break at a certain point. Like for some kinds of inputs, he would note that this program just would produce an error. I mean, if I had written this code, I would just be desperate and do something else. But he was very smart. He actually analyzed all the points, all the input values for which this code would break. And he realized they are on some linear manifold within this four-dimensional space. Then he talked to his old friend Freeman Dyson and told him, oh, by the way, like I'm doing repeated business lemma. It turns out that always when points are on this linear manifold, the code breaks. Can you tell me what's going on? And apparently, like they described this in the blog, apparently the next day Freeman Dyson came back and he presented like the first 2 pages of the manuscript. So the discovery of the zero-determinant strategies is more of a byproduct of finding an error of some code. Yeah. All right. By the way, what was the error in the code? Like at some point, there was a division by 0. All right. How much time do we have? Yeah, we don't have too much time, but perhaps I can still tell you a little bit. So it's quite a bit of a surprise that extortion, that there are these extortion strategies because no one has heard of it. And also they didn't really appear in evolutionary simulation, so we haven't seen them before. But now that you know them, you can actually test, like, would these extortionate strategies evolve? Like, would we see them in simulations? And so what we did then is, like, we did a simulation similar to what Novak and Sigmund did. Again, you have a population. Again, they play memory one strategies. Again, there are mutants that introduce new memory one strategies. And then we explicitly recorded how often do players play extortionate strategies. Now, we cannot do it in this naive way because as I told a few minutes ago, the space of extortionate strategies within the memory one strategies, it's a two-dimensional set within a four-dimensional set. So strictly speaking, it has measure 0. So the probability that a random strategy would be exactly an extortionate strategy is 0. So what we ask instead is, how likely is it that we visit an epsilon neighborhood of the extortionate strategy? So this would have positive measure. All right. So we did this, and what we find here is that things like the relative abundance depends on the population size. What do I mean by relative abundance? We just compare if you have a process with selection where strategies with a higher payoff reproduce more likely. We recorded how often do you then visit the subspace, the neighborhood of extortionate strategies, and we compare it to how often would a neutral process visit this neighborhood. And so in particular, if this relative abundance is larger than 1, you visit this neighborhood more often than you would expect under neutrality. So that's what this graph means. And what you see here is that if the population size is very small, extortionists can evolve. But if the population size becomes larger, then usually you don't see extortion. And perhaps the interpretation is the following. Like, for example, if you write down the payoff matrix between two strategies, like, for example, you might have extortion versus win-steal shift, extortion versus win-steal shift. It turns out extortion versus extortion gets a payoff of 0, because extortion versus extortion, I want to get twice as much as you get, you want to get twice as much as I get, but the only solution to this equation is actually that we both get 0. Now, what is it that extortion, what is it that win-steal shift gets against extortion? Now, it depends on the precise value of the extortion strategy, but possibly it gets something like 0.5, say. Now, we know that extortion against win-steal shift, it gets something larger than 0.5. So, for example, it could be that extortion against win-steal shift gets a payoff of 1. And so, for example, if B equals 3, C equals 1, win-steal shift against win-steal shift, it would always cooperate against each other. So they would actually get a payoff of 2. So what you see is that it is true that if win-steal shift really is matched with extortion, the extortioner gets a higher payoff than win-steal shift. So that is true, like it's a mathematical fact. But what you also see when you look at this payoff matrix, should you really play extortion? And if you look at it with classical eyes, no, you shouldn't. Because 0 is worse than 0.5, 1 is worse than 2. So extortion is actually a dominated strategy. And therefore, in large populations, dominated strategies tend to go extinct. In small populations, they can sometimes survive. The reason is, I call this sometimes the Tonya Harding effect, but probably none of you knows who Tonya Harding is. So this is like perhaps 30 years ago. There were 2 very good ice skaters from the US. They both wanted to go to the Olympics, but they both knew that only one of them can go. And now if you are under such stiff competition, like if you are in a large population, so it's like if there are 100 good ice skaters, the only thing that you can do is like to try to be as good as possible. But if there are only 2 good ice skaters, you can either try to be as good as possible or make your opponent as bad as possible. So you can try to be spiteful. And what happened is actually that the opponent of Tonya Harding, at some point there was an incident and her leg was broken, violently. People actually came to her and broke her leg. It turned out, I believe it was Tonya Harding's boyfriend at the time. So the interpretation here is the population size is very small. It can select for spite. So you don't need to maximize your payoff. You just need to maximize what you get compared to the other player. Okay. Yeah, and the last interesting thing is, so here I looked at evolution within one population. You could also check what happens if there are 2 co-evolving populations. So for example, there might be a population of hosts and a population of symbionts, and they both, like hosts play a repeated Princess lemma with the symbionts. And what happens is, like the outcome now depends on the relative evolutionary rate. So this means just how often 2 hosts reproduce compared to the symbionts, like how fast is evolution in the 2 populations. And what you see here, like this is a simulation, like what you see here is if they both evolve at a similar rate, usually what happens in these simulations is that they would, so this is also hosts and symbionts can choose between memory 1 strategies. So what you would see is that in the end they play something like all D, they would both defect. All right, I'm almost done. But you also see that if the host evolves at a much slower rate than the symbiont, so the host is very slow in evolving. What you see an advantage is that in the beginning there's an advantage to symbionts because they can actually exploit the host. Like the host in the beginning plays something like all C. Symbionts learn, okay, against this host I can just play always defect. But over time, so the host would have a very low payoff. But then over time, the host learns to play such an extortionate strategy. And once that happens, symbionts actually learn that the best thing that they can do against their extortionate host is to cooperate all the time. So once that happens, hosts again have a very high payoff. And then as you see, like hosts become more and more extortionate in these simulations. All right, so that's what I wanted to tell you. I skipped, unfortunately, an experiment on extortion. But that's pretty much it. So some things that you should have learned today is like we used our techniques to explore why people cooperate. So one mechanism for cooperation is this direct reciprocity. So it's this idea that once we interact repeatedly, there can be a very good reason to cooperate. Yeah, that's it. Yeah, as the only strategy, the answer is no, because like usually, if you have such an extortion strategy and everyone plays extortion, like usually Winslow shift, for example, could invade. You might ask yourself, like, is it possible that perhaps there is some coexistence between extortion and all C? Perhaps that is a stable coexistence. To be honest, I don't know of such results. Yeah. Yeah.
What did you mean by the equalizer strategy? One of your plots had then.
Yeah. So to be honest, none of my plots actually had an equalizer strategy, but that is actually another interesting zero-determinant strategy. So what I showed you, I believe, like I gave you two examples of zero-determinant strategies. Like I guess one had a slope that looked something like this. I should make it even clear. Like I believe it had a negative slope. And one of the examples that I told you is at this slope. So those were the two examples I believe that I showed you on some graphs. There is another very interesting instance of a zero-determinant strategy, namely one that has exactly a slope of 0. And these are called equalizer strategies. And the interesting property that they have is, like, I can unilaterally determine your payoff. Like, no matter what you do, like you could be here, you could be here, you will always get the same payoff. Like, you are entirely under my control. And so that's also an interesting subset of strategies that people have been interested in.
So the evolution of cooperation that you were mentioning, is it a very generic statement or is it restricted to human species? That especially this question is coming from the Axelrod Hamilton experiment that you were referring to.
Yeah, no, like people would like it to be a bit more general. So in particular, like people appreciate that there are these examples out there of sticklebacks, of vampire bats, that this is a fear that does not only apply to humans, but that also applies to some kind of animals. At the same time, I should say that like this empirical evidence is sometimes disputed. So there are people out there that say, oh, what the sticklebacks do, it's not really tit for tat, but rather it's something complicated, like it could be relatedness or something like that. Like it's sometimes hard to make a convincing distinction between direct reciprocity and other mechanisms. But I do believe there are a few, like for example, vampire bats, I believe by now is pretty much undisputed that this is an instance of direct reciprocity.
Thank you.
Yeah.
Human systems. So, but how about chimpanzee groups where they have these groups and they raid each other by forming these raiding parties? There at least, I mean, empirically there seems to be a very strong within group aversion to be part of these raiding parties, but then more raiding parties that you have per group, the group does well. So at least in, if not for humans, but other system, would you say group selection is a good argument for evolution of cooperation?
The truth is, I don't know. I know one example where it's definitely not a good argument because I talked to a person who does experiments on that. So there is like the species, I honestly don't know on chimpanzees or apes. There is this one species where people argue that there could be some reciprocity going on, which is Norway rats. So apparently they are able to do some kind of reciprocity with sharing food or sometimes also doing other services, some kind of trade of services. And there are researchers that try to verify that there is direct reciprocity. They have pretty convincing evidence. And I talked to that researcher, like this researcher is called Manon Schweinfurt. She told me pretty explicitly that there's no such thing as group selection in mice. Usually one of the arguments is that there are just no stable groups, like that there's a lot of migration and this kind of stuff. So it doesn't make sense to talk about groups there. Yeah, thank you.